the stimulated absorption would occur with a rate that we call lambda 1 to 2, which is given by a chunk of constants a matrix element that can be calculated from the wave function of the state 1 and state 2. So from state 1 to state 2. And with the R in between, the vector for the position of the electron. And after you calculate this vector, you take the magnitude square, as well as the correct incident frequency. And the transition rate is proportional to the strength or the intensity of that incident light. The U in particular is the energy density of the incident. At the same time, we also found a similar, actually identical expression for stimulated emission between the two same states, given by the same chunk of constants. In principle, this should be R12 square because the initial final are now interchanged. And again, the frequency needs to be right, and it is proportional to the strength of the incident light at that frequency. Okay. However, this is the same as R21 square. That is to say, we found that lambda 1 to 2 is the same as lambda 2 to 1 under the same incidence condition. So this is what we got last time. Today, we will start from here, and then we will go back in time a few years before this quantum mechanical results. We will go back to a result obtained by Einstein before quantum mechanics was established. At this point, I just would like you to take a final look at this quantum mechanical result. In a while, we will call this whole chunk B12. So you will see what Einstein called B12 is what we got in quantum mechanics, this whole thing in front of the U, all right? And then the stimulated emission is what Einstein would call B21. Of course, we know something more than Einstein did. We now know from quantum mechanics some formula to calculate B12 and B21. And at the same time, we know one more thing. B12 equals B21, okay? Now, all these are perturbation results from quantum mechanical formalism. So what I would like to do is to take this result with you, and then we will discuss what Einstein did. So let me look up the right set of notes. So in this part, we will discuss 1917 Einstein's work, especially what popularly called his A and B coefficients. I already mentioned what the B coefficients are, and the A coefficient is the one for spontaneous emission. The question in our discussion now is that we cannot handle spontaneous emission. So we would like to borrow a result from Einstein's work, and then we can copy the quantum mechanical results for stimulated emission and use it in spontaneous emission. So you will see that there's a difficult question, but then we have an easy answer. Okay, so that is the whole idea of this part. So let's move on. For this discussion, I would like you to wind back the time to 1917. That is to say, before Schrödinger, Heisenberg, Dirac, all these brilliant physicists work out quantum mechanics. But Einstein was not ignorant about quantum physics. He was part of it. So let's see, before 1917, what were known. Basically, in this work, Einstein was trying to derive Planck's formula one more time. Planck's formula was the beginning of quantum physics, 1900. So that is the first year of the 20th century. So Planck wanted to explain the thermal emission from anything with finite temperature. Then he got a very nice formula that fit so well, very well to experimental data. That is the Planck thermal radiation formula, usually called black body, but actually thermal radiation may be a better description, because anything like us with a finite temperature would radiate a EM spectrum, and our spectrum may be peaked at infrared. Okay, so that's why at airports you see this infrared detector for your temperature. So what did we know in terms of physics at that time? Certainly we had Planck's formula, and then we know something about photon due to the work of Planck's formula interpretation as well as photoelectric effect. And at the same time, Boltzmann formulated his statistical mechanics. So we know some standard, for example, the Boltzmann factor that I think most of you have already learned in your 3000 level thermodynamics and statistical physics course. A few years forward, Bohr has his atom model. So the Bohr model, in particular, in which in the last statement of his model, he says, for an excited atom, it can come down in energy to a lowered, so he calls stationary state, and the energy difference will be given out as what we saw in the spectrum. Okay, so that is what Bohr said. That is to say, there could be transitions between the levels or the energy stationary states, what Bohr called, to give out or absorb light. Okay, so we are not totally ignorant at that time. We know quite a bit of things at that time. All right, so you will see that all of this played a role in Einstein's work. So to start this section, I would like to remind you of Planck's formula. Planck's formula gives the distribution of anything at finite temperature T. It will radiate a range of EM waves. Usually, say you feel something hot and it is infrared mostly, but there is a spread in frequency. If you look up books, usually it is cited in frequency F in this form, okay? Now, I intentionally write it in a statistical physics form so as to challenge you a little bit to or make connection to what you learn in statistical physics. but I will not explain why I separate the term like this, all right? But basically, you see, there are three different factors. In Planck's formula, in statistical physics language, you will see this is the energy of a photon. This is the thermal factor. For those of you who already encountered Bose-Einstein distribution, this is one special form of Bose-Einstein distribution with the -1 in the denominator, okay? Nonetheless, it means it is how much excitation of a particular oscillator of frequency f at finite temperature T. So this is the degree of excitation. If excited, it carried that much energy, okay? And then the prefactor is harder to explain. It is called how many EM wave modes are there for that particular frequency. In statistical physics and solid state, it is called the density of modes or density of states. But I don't expect you to know all this division of the terms. The key point is that Planck proposed this formula to explain experimental result in 1900, all right? And that works perfectly. And at the end, when he tried to explain his work, he has to invoke something called quanta of energy, HF, that has to do with oscillator. But in our context, we have been using omega rather than F. But that will not be a problem because we know how to change variables. We know that F is related to omega by a factor of 2 pi, all right? So I encourage you to try this exercise. Convert this thing, it's not easy. You have F squared here, F here, another F here, and another F in DF. You have to change several places, okay? If you think you know how to do it, try it. If you hesitate, well, how to do it? Of course, you should try it, okay? That's the advice. If you don't want to try it, you just want to look at the result, I write it down for you. So more in our discussion, we will not use F, but we will use omega. Converting this formula to omega, we will get the same thing. We have an omega square like prefactor, that is the number of moles in the range omega to omega plus d omega. So that is the so-called density of moles. This is a quanta of energy. This is how much quanta there are at a finite temperature T, excitation, that means, okay? So take a last look at this Planck's formula. The EM wave strength, the kind of energy density from omega to omega plus d omega is that much. That is what Planck's formula says. Of course, there are a lot of fascinating physics out of this formula. For example, you integrate out over all omega, that is the total energy radiated given a finite temperature body, that will go to T to the 4th power. That is called the Boltzmann-Stefan law, okay? So that's why, you know, Boltzmann must have had played a role in this kind of business. And now, just to remind you, Bohr said stationary state, transitions that will give out or absorb light. All right, so there are interactions, even in Bohr model, between different states of the matter and light, as we have been discussing in this module. And now let's go to Einstein's work, 1917. His primary goal is to revisit the Planck's formula. So his thinking is something like the following. There's a cavity wall, there are many atoms, so those are matter. Inside the cavity is full of EM waves, the radiation part. Thereby, in this system, the atoms are constantly interacting, exchanging energy through absorption and then emission. That is to say, in thermodynamics idea, these processes let the matter part and the radiation part equilibrate. They can become equilibrium at a temperature T. So that is the idea. So just like what we did before, instead of discussing the whole spectrum of possible transitional energy, we just pick two states from the matter system, and then we consider a system in which this two-state system, there are many of them, and then at the same time, we have this radiation, EM wave, surrounding it in the environment so that they could exchange energy and achieve an equilibrium state. Okay, so that is the whole idea. So simply put, for those of you who learn thermodynamics, statistical physics, we used to have a system like this with a wall, cannot interact with the surrounding, but then inside which we have some atom state with two levels, and then the background is now full of EM wave. They could interact, exchange energy, and equilibrate at the temperature T. Okay, so that is the standard setting in statistical physics. So now we start Einstein's journey into something fascinating. The first thing he knew, and that was established at that time, was that given there are two levels for the matter, for the atom part, let's say there are N1 atoms in state 1 that has a lower energy, E1, and N2 atoms in state 2, and the total number of atoms is fixed at N1 plus N2 in the system, all right? So now, if the system is at a temperature T, what statistical physics tells us is that the number N2 is proportional to this Boltzmann factor. The energy of that particular state is up here, all right? Similarly, the number of atoms in state 1 is proportional to this E minus E1 over KT. Thereby, the ratio must be this ratio, canceling out whatever that is proportional in front. And the punchline is, as long as equilibrium is achieved, this ratio, number in the higher state over the number in the lower state, is given by this Boltzmann factor. Okay, that is the only thing I want you to know or to take in from thermophysics. And we defined this difference as h bar omega. That is the right incident frequency that we need to excite or stimulate emission, all right? So this is the piece of thermophysics that Einstein used in his work. And I believe you have seen this in your thermal course, have you? Up to this point, have you done this? This is Boltzmann, huh? Okay, good. But the punchline, okay, look at this thing. This is higher energy over lower energy number. It is often that you have more in the lower energy than the higher energy one because of this Boltzmann factor. Okay, now this is a good piece of physics to keep in mind. Now, Einstein wanted to get the Planck's formula. That is his goal. We visited. Therefore, in a way, the answer was no. He wanted to get this. Okay, that's the goal. All right. So whatever he did, he already know what he wanted to get. Especially, he wanted to get at this -1. It turns out that it's not easy. All right. So now, in order to get the -1, I think he must have tried some other ways that the -1 was missing. Then he got the right version. In order to get this -1 in the denominator, he needed 3 processes. Not 2, but 3 processes. The 3 processes that he invoked in his work are the following. Very ordinary, right? The first one is absorption. So there are 2 levels, lower, higher. When h bar omega comes in, the photon is known, okay? He was responsible, photoelectric effect. So when the energy is right, there can be absorption. That's what Einstein said, ordinary. And actually for many years, it was known that if you put a system at a higher energy state, you don't do anything on it, it will come down and emit anyway. You don't need to do something. That is spontaneous emission. So there's no incident thing, only they come out and there's something out. All right. Now, these 2 processes were ordinary at that time, we know. Okay. Just to remind you, in terms of Schrödinger quantum mechanics, this is difficult to handle. We want to handle it now. But in order to get this -1 in the denominator, Einstein had to propose a new phenomena. That is called the stimulated emission 1. Okay? He said there should be a possibility of the following process. Something in, but the atom is already excited and then stimulated another emission by the incident h bar omega. So there are 2 lights out, right? 2 photons out. Now, you must appreciate this process was not known to physicists before this work of Einstein. That's why when many people regarded Einstein as the proposer of this stimulated emission process, and then even pushed him to be the discoverer of he invented laser. But I must say that was something like 50 years apart from his work to a working laser. Okay, that may have stretched the contribution a bit too far. Nonetheless, it's true. Einstein's work proposed this new process. That is absolutely true. So let's take account of what we know in our quantum mechanics course. We know something quite different, okay? We know this quantum mechanically. We know a formula. And we know that even under one formula, they are the same, okay? But we have difficulty in deriving a formula for spontaneous emission. So that is quite different from Einstein's situation. Everybody knows this too. He proposed a new one, all right? That is the thing. So now let's make connection and then move forward. First process, stimulated absorption. Since it is stimulated, that means the probability of that happens per atom per unit time, that's what Einstein considered, must be proportional to the stimulation. Otherwise, it will not be called stimulated absorption, right? So that is natural, proportional to the surrounding incident light, at that particular required frequency. Okay? By proportion, it means we can introduce a proportional constant. And that's how Einstein's first B coefficient enters. It is called B12 at this point because it means absorption from 1 to 2. So summary, probability of absorption per atom per unit time. You see there is some rate here. Is B12 times the energy density of the EM environment at that frequency. Okay? That is Einstein. How about Schrödinger? What we know, okay? At the beginning of today, I already remind you of that. We know the B coefficient. This is the per atom per unit time. We work on one atom and then divide the time through, we got lambda. So this is exactly what this thing is about. Okay? And therefore, this is our result for B12. All right? So you must appreciate what you know. You already know something that Einstein didn't know. The second process, spontaneous emission. By that, of course, we mean we don't need to stimulate it. Therefore, the probability per atom per unit time should not depend on the U term anymore for this process. So Einstein just introduced an A. It is emission, so from 2 to 1, that's why I label it A21. Okay? How about Schrödinger quantum mechanics? That is our weak point, right? We cannot handle it using Schrödinger quantum mechanics. It can be handled by quantum mechanics, but we need to quantize the EM field. So we need quantum field theory that is beyond our scope. But we will see. By borrowing Einstein's relation, connecting his A and B coefficient, because we know B, therefore we know A without any effort. That is the approach. How about the new thing that Einstein proposed, stimulated emission? Same thing. Because it's stimulated, it must be proportional to U. And therefore, Einstein introduced his third coefficient called B21. Because it is emission from 2 to 1. At this point, there's no relation between B12 and B21. But our quantum mechanics knowledge, no, because we know an expression for lambda 21. And we know that it is true. Therefore, we would expect Einstein to get B21 equals B12. Okay? But at this point, this relation is not known. It is yet to be discovered. So let me summarize. We consider three processes in the Einstein's approach: stimulated absorption per atom per unit time, spontaneous emission per atom per unit time, stimulated emission per atom per unit time. Okay, so now we already mentioned how temperature can enter into the discussion. At thermal equilibrium, number up there over number down there must be of this factor. All right, so let's put everything together now. Our system has atoms that can be in 1, in 2, constantly interchanging energy with the surrounding EM background. Therefore, let's look at what equilibrium means. Equilibrium actually is a dynamical situation. At every moment, atoms will be excited up. It will do emission, either spontaneous or stimulated, and come down. Only that at equilibrium, the number up there over the number down there is some constant factor fixed by the temperature and the energy difference. Okay, so that is the whole physics. Let's write this physics out. Equilibrium means going from 1 to 2 up is balanced by the number that is going down from 2 to 1. That's it, right? That's why you keep some constant ratio. So let's write it down. Number of atoms going up, that is only one process, stimulated absorption, must be balanced by number of atoms that coming down through stimulated emission and coming down through spontaneous emission. Okay, so I pause here because that is the physics. The rest is just some formula. Okay, do you understand this statement? It's like a reaction. It's like a chemical reaction. Okay. Now, if you understand that, then there is no more difficulty or the pages to follow. Okay. So let's see. Left-hand side, number of atoms going up due to absorption. So you have that many atoms down here. Per atom per unit time, that many will go up, the probability that will go up. So for a tiny time interval, you can think about it, you have that many going up. Okay. Similarly, you have N2 up there. For stimulated emission, you have that many coming down. But for the spontaneous one, that does not depend on the surrounding strength of the radiation, is just using its own rate. Okay, so now 30 is the mathematical way of writing down this statement. Okay, do you understand? Is that okay? Okay, I think it's rather beautiful piece of work actually. Now the rest is just simple. Now we have N2 that can be factorized out on the right. Divide the N1 to the bottom. Okay, therefore you solve this thing. Follow me? That's easy. So this equal sign comes from this equation, the balance between exciting up and coming down. Then we also know from Boltzmann's work, equilibrium, the number must be like this. Now that is a brilliant step, I would say. Okay, that will be a good question in your thermal and statistical physics course, actually, a good exercise. Okay, so now you must appreciate this line, I use all the physics. First equal sign is about balancing the processes. Second sign is from statistical physics at equilibrium. All right. Therefore, we have an equation that connects Einstein's AB coefficients, the surrounding radiation already at equilibrium with the atoms, and the temperature, okay? And the energy difference between the two levels, omega, which is E1 minus E2. Therefore, we can solve this U out in terms of all these variables, okay? So 31 is the punchline of the discussion so far. The left-hand side is what should be the Planck's formula. The right-hand side is what Einstein got up to here. His coefficients, okay? Just to remind you, A, spontaneous emission. What he know, everybody know quite well the phenomena, but we don't know quantum mechanically. B, 1, 2 is this absorption, ordinary. But he needs, now that is the point you should pay attention to. He needs to introduce a new process, new at that time, called stimulated emission, the B21, in order to get something here, you see. That's why I said, I guess, he must have tried without the spontaneous, without the stimulated emission, then he got just this term, and then he couldn't get the Planck's formula. That's what I guess, okay? So now you see something already like the Planck's formula. So the point now is to make sure that this will give us this, because this is the answer that he should get, okay? So now, here is the dirty part. Look at this derived form and the expected form. Therefore, you can start to collect results. First thing, these two must be the same. Therefore, you can pull it out and you get the -1, the so-called Bose-Einstein distribution. Okay? So do you get the point? Okay? Được chưa? Okay? Now there's some brilliant things here. In order to get the Planck formula, we need the B12 equals B21 equals, we can represent it by a single B, all right? But that is right? That is right even in Schrödinger's quantum mechanics. We don't need to refer to thermal stuff, but we already derived this through time-dependent perturbation theory. So that's pretty nice. If this is not true, we cannot get this factor. Okay, now that's why I rewind the clock for you. This is 1900. Okay, so this is 1916, I think. That's when Einstein did the work. In order for this to be in line with this, therefore, we must have that. Is that okay? Okay. I think that is reasonable step to do. Okay. But don't be carried away. Even Einstein knows this. He did not know the formula. Okay, he has to wait for a few more years. But the point is that due to equilibrium processes and due to this experimental fact, the stimulated emission and stimulated absorption rate must be the same. Then, what's more, if you do that, you can pull out a prefactor and then you got this, right? Rather nice. Therefore, the prefactor must go with this thing. You see? Okay, and that is what we are looking for. Suddenly, we have a relation between A over B. At this point, I will simply write the Einstein coefficient into A only, not A21, okay? Just save the indices. So we have A over B being this factor, okay? So therefore, we have that. The point here I would like you to note is the ratio goes like omega cube, okay? That has some physical consequence later. Nonetheless, we don't need to care about that at this point. We have a relationship between A and B coefficients, okay? Now that is where we can make use of Einstein's result. We have difficulty finding A, but we already know B. Now Einstein told us that A is nothing more than this factor multiplied B. Therefore, using Schrödinger's result of B, we know a result of A, okay? So following the approach, the idea, okay? So we are done. This is the key result that we will use and move on. And the next point is this omega cube thing. Basically, it says the following. This is the one, state number one, all right? The point is, state number one, if you have higher state here, big energy difference, spontaneous emission rate here, compared to another, say, even high in energy, this is very unstable, okay? The higher one will be more unstable. That is the whole thing, because omega is this energy difference, okay? Divided by h bar, all right? So you see omega to the cube, spontaneous emission rate, okay? That means the excited state of higher energy, the rate will be higher. It will tend to go down sooner than an excited state that is not that high in energy, above state one, okay? Simply put, 高處不勝寒, okay? So the higher the excited state, even spontaneously, you don't need to do anything to it, it will tend to come down, okay? That is what this term means. And not to a single power, it goes omega to the cube. As I mentioned, this cube actually has two contributions. One is an omega due to some photon energy h bar omega. Another omega square comes from the dimension. It is a three-dimension system. I'm sure you will encounter this thing in your statistical physics course. It is called density of moles or density of states, okay? Pay attention when you come to that part. Simply put, the higher excited state will come down faster, that is more readily, okay? Therefore, if we are, like this is a rate, therefore A is 1 over time, okay? Therefore, some time is 1 over A, right? Okay, and that is called the lifetime of that excited state. This factor means the higher excited state will have a shorter lifetime. Okay, so this I already mentioned. So finally, let's take Einstein's result, and then suddenly we even know the formula for spontaneous emission. Okay, So that ends the discussion on Einstein's AB coefficient. So let us write something out explicitly. From Einstein's discussion, A is a factor times B, and we know B. Therefore, we can write down an equation for A coefficient. Remember, it is per atom per unit time about spontaneous emission. That's it. It does not have a U that goes into the lambda, all right? So it has an omega cube factor. This is dimensional dependence, 3D system. Again, it depends on this matrix element that we discussed about the selection rule. I already mentioned that 1/A is a time. It is the lifetime of an excited state. It is related to it. Why it is so? Then we can do something that you learn in high school. You learn this mathematics in nuclear decay, but it's the same thing, okay? It's not nuclear decay, it is decay of excited atoms. So if you have N2 excited atoms at some time, then in dt time, the number that will have dropped, decayed down, will be per atom per unit time, how many you are there times dt. Therefore, you divide the dt through, you get this differential equation. This can be integrated. You take the dt to this term, take the n over to this side, you get a log, therefore you get exponential. So you see this exponentially decaying solution. Thereby, 1/A must be a time constant. This is the lifetime. That back up my claim that this is related to lifetime. But actually, the lifetime of an excited state is more complicated than that, because an excited state may decay to here, to here, to here. There may be many lower states that this excited state can decay to. Therefore, we need to sum up all these possibilities. Nonetheless, if the 2 only has one state 1 to go to, we can calculate lifetime explicitly. And this is a point here that I want you to appreciate what quantum mechanics is. I mentioned this several times. Don't take quantum mechanics as many formulas with variables with symbols. Quantum mechanics, one of the triumphs, the major triumphs, is to calculate some number out that can be compared with experiments. And this is one of them. We have already seen that we can calculate selection rules, or even the lines is brighter or dimmer. Okay, this is another key result. We can actually calculate the lifetime of the state. All in all, we only need to know 2 things. Where does the excited state decay to? That will fix the omega. And then the initial and final state wave function, and in between electrons position operator R. Rather magical, okay? Well, this week the TA already calculates something 1s to 2p to u in hydrogen. So one more comment is that now, usually if you have allowed it transition to a lower energy state, that will mean spontaneous emission will occur rather readily. The lifetime of this state will be short, okay? A typical short lifetime thing is this is a ballpark, okay? 10 to the minus 8, 10 to the minus 9 second. That is the excited state lifetime. You don't need to stimulate it, it will come down. But sometimes you will see some weakly allowed transition. That is to say, the element is not that strong, the matrix element is not that strong. That could have some excited state with this kind of 10 to the minus 3 second lifetime. And those are called metastable state. For hydrogen 2p, it is of the order 10 to the minus 8 second, okay? Because there is a 1s to go. This is hydrogen 2p, 2p state. I mentioned this to be more formal. If this is the excited state and there are many lower states that it can go into, then the analysis is that you put more terms in the decaying analysis, and therefore each of these processes will contribute a rate. So you have this being the lifetime of that excited state, regardless of where it decay to, all right? And then, of course, it will mean 1 over this, the rate, okay? The total rate is given by that, all right? So you see it's something like resistor in parallel or in parallel, right? Okay, so that means you have to add up this contribution. That is formal. But when you see this, you already see that the smallest one will dominate, right? The smaller one will give you the biggest one, so that you flip it, that will be the best estimate. So I already mentioned what is short. Okay, you want to see this calculation, look at the sample question, and then sometimes you will see some longer lifetime. And that will be useful for some purposes like selecting a state, preparing for lasing action. So that ends this part. I will take a break here, and then after the break, there will be a short discussion on laser.